Thank you. Thank you, introduction, Sano-sensei. So good afternoon, everyone. So I would like to thank to organizer from inviting me to this symposium. It's a honor to be here today. I'm Kenji Tanaka from the Device Innovation Center at the NTT ION Innovation Center. This title of my presentation is shown the slide. So let's move on the agenda for my presentation. First, I will start by discussing the current state of data centers and the increasing need for geographical distribution. And next, I will introduce the ION and APN, which are entities innovation, infrastructure, and network service designed to address these challenges. Then we will discuss the development status of APN and some interesting use cases. Finally, I will focus on my research to expand APN's potential. These research topics highlight our effort to further enhance the capability and applicability of ION and APN. Let's start with the slide. So, as you know, data center market is expanding significantly. This rapid growth is mainly driven by the very first growth of AI-related services. Let's look at the left graph. This graph is about AI infrastructure demand in Japan for storage and servers. You can see demand for both is going up a lot from 2023 to 2030. AI infrastructure needs are growing very fast, about 10% per year. In summary, this graph clearly demonstrates the strong and accelerating growth in data center demands. So now I will report on the potential challenges regarding data center infrastructure in Japan, the graphical barriers and associated risk. So by comparing data center distribution between the US and Japan, we observe a difference. So in the US, data centers are more geographically spread, even in areas with many data centers. Like California, it's just about 14% of the US total. However, Japan is different. As you can see on this map on Japan, about 88% of data centers are concentrated in Kanto, this area, and Kansai, in this area. This concentration makes risk. So the first risk is natural disaster, especially earthquakes. Japan has many earthquakes. If data centers are concentrated, a big earthquake can cause big data center troubles. And a second risk is power. Data centers use a lot of power. They are all in Kanto and Kansai. The power grid there can become weak. The Japan's government understands these risks. They are trying to encourage data centers to spread to areas like Hokkaido, this area, and Kyushu. So promote geographically distribution data centers, an NTT has launched the ION project, which stands for Innovative Optical and Wireless Networking System, and is driven initiative to collect data centers. At its core is the all-photonic network, APN, which drives low latency, high capacity connection between the data centers. This distributed data center approach, enabled by ION and APN, offers numerical benefits as listed here. So by distributing the data centers, we enhance resilience against disaster as localized event will less impact to the overall infrastructure. And we aim to process data in region with abundant clean energy sources, such as solar and wind power, further contributing to sustainability. So now dive into core technology of APN. APN is dedicated communication services that use optical wavelengths to connect endpoint. So unlike traditional network, it provides end-to-end optical paths and low latency jitter. So So as highlighted here, low latency are essential for effective collaboration between geographically distributed data centers. NTT is promoting APN through the ION Global Forum and exploring RDMA over APN for research and development. These graphs show actual RDMA performance over APN. The left graph displays RDMA light throughput using NIC offloaded Locky version 2 for host memory to host memory transfer. So even over long distance RDMA, up to 1,000 kilometers or more, APN achieve a near theoretical thread speed of about 100 Gbps. So to show you the APN is actually working in Japan and internationally, so we are proud to announce that we have launched the international APN connection linking Tokyo to Taipei. So this connection span approximately 3,000 kilometers and provide a bandwidth of 100 Gbps. Remarkably, the network latency is only 70 milliseconds. This is an exceptional value, achieve about 60% of the theoretical speed of light. Briefly, so we are expanding our APN network sequentially across Japan and have also started services in the US and UK. So next, we look at some future use case of APN and how it can be used to solve scientific challenges. So the project concept is straightforward yet powerful, connecting major research facility and a high-performance computing data center in real-time connection using APN. So in large-scale scientific experiments, researchers generate a numerous amount of data daily. Usually, analyzing scientific big data has been an offline process. However, APN enables real-time data analysis by providing the bandwidth and low latency zeta needed to transmit these massive data sets to data center for immediate processing. By analyzing data close to its generation, a researcher can get real-time insight and feedback from their experiment. This allows them to accelerate research cycle significantly, making adjustment and refine experiments on the fly. We believe this real-time capability brings a significant benefit for researchers. Okay, so as I said in agenda, so the last part is about my research to make APN more powerful and useful. In the next slide, I will explain my research in detail. So so I focused on the first research theme, privacy for long-distance RDMA over APN. So as APN expands to support long-distance RDMA, privacy is important. So the main issue is a Locky version 2, an RDMA protocol was originally designed for secure, trusted data centers. It's therefore lack built-in encryption. Now, a straightforward plan is to run Locky v2 over IP and IP layer encryption, like IPsec. However, this IPsec remove RDMA's main benefit, bypassing CPU processing overhead. So researchers are exploring a new way to encryption RDMA without losing its performance advantage, but no clear standard has emerged. Our work aims to solve this by using hardware-accelerated IPsec placing IPsec functionality direct in network hardware to keep RDMA performance. So previous study, Microsoft Azure provides an excellent example of efficient network function processing using SmartNICs by offloading various network tasks, include IPsec, to disaggregated SmartNIC. So this shares stateful network function processing pool. They can load balancing packet flow and improve network performance without overloading CPU cores. They use disaggregated architecture combine the stateless switch and stateful SmartNIC. This design lets switch handle basic routing with a SmartNIC, handle more complex stateful data flow processing. So we learn from Azure's approach and extended this idea in our work. So it's a proposed side. Microsoft Azure's approach is insightful but has drawback for high bandwidth VPN scenario. One issue is that connection-based load balancing only happened at the start of each connection, which failed to adapt to shifting traffic pattern during the connection's lifespan. This can cause uneven load distribution and congestion on certain SmartNIC. Another issue is each VPN connection still rely on the bandwidth on the single NIC, which become a bottleneck for APN. So to address these challenges, we propose a disaggregated system with a stateful switch and stateless FPGA NICs for hardware acceleration IPsec. The switch performs packet-level load balancing and can aggregate data flow from multiple FPGA NICs, effectively increase the maximum available bandwidth for IPsec communication. So let's look at the diagram, the data flow. So first, the endpoint, a TCP packet data flow sent from endpoint into the programmable switches. Next, the programmable switch analyzes these packets. It examines the packets to determine the necessary IPsec processing based on pre-configured security policy. Then the programmable switch dispatches the packet to multiple FPGA NICs with encryption circuit. This is where the packet level load balancing comes into play. These FPGA encryption accelerators process the packet in parallel. Each FPGA works to perform the computationally intensive encryption tasks in hardware, achieving high throughput and low latency. So after encryption, the programmable switch collects the processed packets from the all hardware accelerators. It then rewrites the IPsec packet header to ensure each packet is directed to the correct IPsec tunnel, adjusting the necessary header field before forwarding the packets. By splitting IPsec encryption tasks across multiple FPGAs and programmable switch for detailed packet handling, the architecture achieves both fine-grained load balancing and high bandwidth IPsec VPN performance. So we compare the throughput per CPU core for two scenarios and found that our method delivered a significantly higher throughput of 33.59 gigabps per core. This performance is almost on same with regular Linux communication that does not use IPsec. Identified minimal additional CPU role for IPsec, in IPsec. Next, so we examine the latency by measuring the result from a 1,000 ping-pong test. The latency distribution graph shows that our hardware-accelerated IPsec has a latency very close to regular Linux communication. This one and this one. So which is especially important for latency-sensitive application. So as for current state, we have successfully verified the principal use is TCP. So and now adapting our design for Loki version 2 over APN. In our second research theme, we explore how to use GPU's efficiency over APN. One of APN's key benefits is the ability to place energy-intensive AI data center in region with abundant renewable energy, easing the power burden in metropolitan area. However, ION's goal of real-time AI workload demands latency under 10 milliseconds, which is difficult when data centers are spread across large distance. Furthermore, this becomes curious when connecting the previous slide, a large-scale experiment phase facility and high-performance computing center in real time. So looking at the latency breakdown pie chart in AI inference serving, the total latency is 6.25 milliseconds. So its inference is so ResNet 50, part size 1, and using the L40S NVIDIA GPU. So this observation is based on, so ResNet 50 is a modest size AI model. So the 10 millisecond constraint will be extremely challenging to meet with more larger model. About a third of the total inference time is overhead, primarily due to CPU-GPU data transfer and inference serving, control, processing, and managing inference. Therefore, by streamlining both the data path and the control path, we can lower these overhead and make remote GPU usage feasible and efficient over APN, even for demanding real-time AI application. So where there is a significant amount of research on low-latency remote GPUs, many existing solutions require a proprietary library or driver that are not ideal for open data centers, where diverse workload and standard interface are the norm. These solutions are also designed with a data center environment in mind. So where networks are typically low latency and high bandwidth, and they do not account for the challenges posed by long-distance network like APN. So our proposed solution is designed to fill this gap. So by removing the CPU from the critical data path and control path, so we reduce overhead and achieve the low latency required for a remote GPU inference over APN. So we accomplished this by deployed AI model in the remote GPU memories instead of loading a model each time an inference request arrives. We keep the model ready in the GPU memory so that new requests can start running immediately. The request and input data are sent directly to the GPU's memory. To make this possible, we rely on several NVIDIA's technology, CUDA graph. So CUDA graph lets us compile multiple kernels into a single graph stored on the GPU, so they can be triggered with a single request. Docker flow handles the incoming packet on the DPU, and the Docker GPU net I/O move input data directly into GPU memory and execute the CUDA graph. So this is our system architecture, combine the Docker and the CUDA to optimize GPU and DPU-based processing, so while completely removing the CPU from the inference pipeline. So in scenario, the DPU and GPU collaborate to manage. So DPU controls the GPU CUDA kernel execution. So the step one, incoming the packet, Docker flow inspecting incoming packet and identify which one require inference. GPU direct RDMA async transfers these packet through GPU memory, direct through memory. Step 3, so Docker GPU net I/O launches the first received CUDA kernel. Received kernel launching by Docker GPU net I/O manages the incoming packet directly in GPU memory and confirm that all necessary packets have arrived. Then merged them into the complete input images. So the received kernel then launches a preload AI model in GPU memory. AI models, so CUDA graph tail launched the AI model. Tail launch allowed for efficient chaining of kernel execution with GPU, further streamline the inference process. The launched AI model performs inference on the input image. The preload CUDA graph executes efficiently with the GPU. The output is passed to the second kernel, and send kernel. Once inference is complete, the results are passed to the send kernel and output process. Okay. The send kernel segmented and okay. As you can see, receive processing and inference processing, send processing are all pipelined. We have successfully pipelined the entire packet inference serving process. Furthermore, we have succeed in the operating multiple model concurrently execution. So this pipeline and parallel inference combined with the CPU bypass achieved through Duca GPU NetIO and GPU Direct RDMA. So significant throughput improved compared to the traditional inference serving method. So we tested our remote GPU system and found a big drop in inference overhead. So down to just 0.43 millisecond. So 2.25 millisecond to 0.43 millisecond. So we also showed that image pre-processing and post-processing can run inside CUDA graph, keeping everything on the GPU and lowering CPU involvement. When we measured throughput using YORO-V4, we saw 173% increase compared to conventional GPU inference serving. Power efficiency also low, with 114% improvement in throughput per watt. Highlight our design advantage for large-scale AI deployment. This result is a key step toward practical real-time inference in geographically distributed environment. So we are currently optimizing the overall system for even greater performance. So this is the last slide. NTT is always making APN better with more research. Remember, some research I talked about is still being developing. It's not in the production APN service. But NTT really want to keep improve APN and ION. My research today showed this. Thank you very much for listening.